The universe had a beginning. Every scientist agrees on this fact, but nobody can explain what came before that beginning. You might think this sounds like a simple question. It's actually the most impossible question in all of science. Tonight we're discovering why the universe's origin story has no first page, and why some brilliant scientists now believe something existed before time itself began. Before we dive into this cosmic mystery, drop a comment about what you think existed before everything. If you enjoy these explorations of reality's edge, consider subscribing. Picture every galaxy in space racing away from every other galaxy. This happens right now all around us. Scientists can measure these speeds with incredible precision. Now imagine running this cosmic movie backward. All those racing galaxies start moving toward each other instead. They get closer and closer together as time reverses. The math leads to one stunning conclusion. About 14 billion years ago, everything in the entire universe occupied a single point. Not a tiny ball or a small region, an actual mathematical point with zero size. Every star, every planet, every atom that would ever exist. This discovery created physics' most embarrassing problem. Our best theories can trace the universe's history backward with amazing accuracy, but they completely break down at this final moment. Before this point, science offers no answers whatsoever. Scientists have a name for what happens at the universe's beginning. They call it a singularity. That's when mathematical equations produce answers that say infinity instead of real numbers. Think of it like this. Imagine trying to divide any number by 0 on a calculator. The calculator can't give you an answer because there isn't one. That's exactly what happens when physics tries to describe the universe's first moment. At this point, matter becomes infinitely dense. Temperature becomes infinitely hot. Space becomes infinitely curved. But nothing in the real world can actually be infinite. When equations start spitting out infinite answers, they're basically admitting they don't work anymore. The math is telling us we're missing something crucial about how reality operates. This isn't just a small problem scientists can ignore. It's a complete theoretical breakdown at the most important moment in cosmic history. Here's something that will mess with your brain. The Big Bang didn't happen at some moment in time. The Big Bang was the moment when time itself began. Most people think time has always existed, like an endless river flowing forever. But Einstein showed us something shocking. Time isn't separate from space. They're connected as one thing called space-time. If space began at the Big Bang, then time began there too. This creates an impossible question. What came before the Big Bang if there was no before to speak of? It's like asking what's north of the North Pole. The question itself might not make sense. Yet this raises an even deeper mystery. If time began with the universe, what caused the universe to begin? Every effect needs a cause. But causes require time to work. Without time, the very concept of causation breaks down completely. Every event you've ever experienced had a cause. You flip a switch, the light turns on. You drop a ball, it falls down. This seems like the most basic rule of reality. But the Big Bang appears to violate this fundamental principle. Here's an event that created everything. Space, time, matter, energy. Yet it seemingly had no cause whatsoever. This drives physicists absolutely crazy. In normal science, you can always ask what caused this, and get a meaningful answer. Lightning is caused by electrical charge buildup. Earthquakes are caused by moving tectonic plates. But ask what caused the Big Bang, and science goes silent. Some scientists argue the question is meaningless because causation requires time, and time didn't exist before the Big Bang. Others believe something must have triggered the universe's birth, even if we can't detect it. This puzzle sits at the heart of modern cosmology like an unsolvable riddle. Einstein's theory of general relativity is one of science's greatest triumphs. It explains how massive objects bend space and time. It predicted black holes decades before we found them. It describes the universe's expansion with stunning accuracy. But this incredible theory has one embarrassing weakness. It completely fails at the universe's beginning. General relativity works by describing how matter and energy curve spacetime. The more matter you pack into a region, the more spacetime bends. But at the Big Bang, infinite matter gets packed into zero space. This creates what mathematicians call a breakdown. The equations produce nonsensical results instead of meaningful predictions. It's like having a perfect map that turns blank right when you reach your destination. Einstein himself knew his theory couldn't handle these extreme conditions. He spent his later years searching for a more complete theory that could. He never found it. Neither has anyone else. Physics has two spectacularly successful theories. General relativity describes gravity in the large-scale universe. Quantum mechanics describes atoms in the microscopic world. These theories work perfectly in their own domains. The problem: they completely contradict each other when both apply to the same situation. At the universe's beginning, both theories should be equally important. You have the entire cosmos compressed to quantum scales. Gravity becomes incredibly strong while quantum effects dominate everything. But when scientists try to combine these theories, the mathematics explodes into chaos. Each theory makes predictions that contradict the other. Neither can accommodate the other's basic principles. It's like having two different languages that both claim to describe the same reality, but they disagree on what that reality actually is. Until physics develops a unified theory that merges both, the universe's beginning remains forever out of reach. The most ancient light in the universe comes from something called the cosmic microwave background. This radiation fills all of space and carries information from the universe's early history. But even this oldest observable light comes from long after the Big Bang itself. It shows us the universe when it was already several 100,000 years old. Before this time, the universe was completely opaque. No light could travel freely because space was filled with a dense fog of particles. It's like trying to see through a thick cloud. This creates an observational horizon that science cannot cross. Direct observation stops at this wall of fog, leaving the universe's true beginning forever hidden from view. Even our most powerful telescopes and most sensitive detectors cannot pierce this veil. The first moments of cosmic history remain as invisible as if they never happened. Science must rely on theory alone to guess what occurred in those crucial early instants. The universe has a very special geometry. It's almost perfectly flat, not curved like a sphere or bent like a saddle, flat like a piece of paper extended in all directions. This seems like no big deal until you realize how unlikely it is. For the universe to be this flat today, its initial conditions had to be fine-tuned to extraordinary precision. Imagine balancing a pencil on its tip. A tiny push in any direction and it falls over. The early universe was like this pencil, except the balance had to be perfect to trillions and trillions of decimal places. If the universe started even slightly more curved in either direction, it would have either collapsed immediately or expanded so fast that no structures could form. No stars, no galaxies, no planets. No anything. The odds of this happening by chance are essentially zero. Yet here we are in a perfectly flat cosmos. This suggests something very special about the universe's initial conditions that current Big Bang theory cannot explain. The cosmic microwave background radiation has the same temperature everywhere you look, to within tiny fractions of a degree. The entire observable universe started with identical conditions. This creates a mind-bending puzzle. Different regions of the early universe were separated by distances so vast that light couldn't travel between them. They had no way to communicate or coordinate their temperatures. It's like finding that every house in a city has exactly the same temperature, even though none of the houses are connected to each other or have any way to share heat. In normal physics, objects only reach the same temperature by exchanging energy over time. But these cosmic regions never had time to exchange anything. They were too far apart and the universe was too young. Yet somehow they all ended up with identical properties anyway. Standard Big Bang theory has no explanation for this cosmic coordination. Something must have synchronized these regions before the Big Bang itself. But what? The universe began with incredibly specific starting conditions. The density was just right. The expansion rate was perfectly calibrated. The distribution of matter was precisely tuned. Change any of these initial settings by even tiny amounts, and you get a completely different cosmos, one that can't form stars or galaxies or support any kind of complex structure. It's as if someone carefully adjusted thousands of cosmic dials to exactly the right positions before pressing the start button. Some scientists calculate that the odds of getting these conditions by random chance are less than 1 in 10 to the power of trillions. That's a number so small it's essentially impossible. This fine-tuning problem suggests that either we're incredibly lucky, or something about the universe's beginning was far from random, but standard Big Bang theory offers no mechanism for this careful calibration. The initial conditions must be taken as given, without explanation. Science works by testing theories against observations. You make predictions, gather evidence, and see if reality matches your expectations. This method has revealed most of what we know about the natural world. But the universe's origin story can never be tested this way. We can't rerun the Big Bang in a laboratory. We can't observe other universes to see if they began differently. This creates a fundamental crisis for the scientific method. How do you verify theories about events that can never be repeated or directly observed? Some scientists argue this pushes cosmology beyond science into philosophy or mathematics. Others believe indirect evidence and theoretical consistency can substitute for direct testing. The universe's beginning represents the ultimate frontier, where science meets its own limitations. Beyond this boundary lies a realm where our most powerful method for understanding reality simply cannot reach. Normal expansion can't solve the universe's biggest puzzles. When galaxies move apart gradually over billions of years, they follow predictable patterns. But this gentle spreading creates more problems than it solves. Scientists discovered that something far more dramatic must have happened. During the universe's first moments, space itself expanded faster than anything physics had ever seen before. This wasn't matter moving through space. This was space itself growing explosively. In just a tiny fraction of a second, a region smaller than an atom became larger than a grapefruit. That same region kept growing to the size of our entire observable universe. This kind of growth makes every explosion you've ever seen look like slow motion in comparison. Regular physics breaks down completely at these speeds. Nothing can move faster than light through space. But space itself has no speed limit when it comes to expansion. Something had to power this incredible expansion. Regular matter and energy couldn't do it. They actually slow expansion down through gravitational attraction. Scientists needed to find a completely different kind of energy source. They discovered it in something called a scalar field. Think of this like an invisible energy that fills all of space. This energy field works exactly opposite to normal matter. While regular matter pulls things together through gravity, this special field pushes space apart with incredible force. The more of this field energy you have, the faster space expands, and the expanding space creates even more field energy in return. Physicists call this energy source the inflaton field. It's a quantum field that exists everywhere in space, like an invisible ocean of expansion energy. When this field releases its stored power, it drives the explosive growth that created our universe's structure. You probably think empty space contains nothing. This intuition is completely wrong. Even the most perfect vacuum still contains hidden energy. Quantum mechanics reveals that empty space actually bubbles with invisible activity. Virtual particles pop in and out of existence constantly. Fields fluctuate up and down even when nothing seems to be happening. This creates what physicists call vacuum energy. But here's where it gets really strange. Sometimes space can get trapped in a fake version of its lowest energy state. It's like water that should freeze but stays liquid because it's perfectly still. The vacuum thinks it's empty, but it's actually loaded with stored energy. When this false vacuum finally transitions to its true ground state, it releases enormous amounts of energy. This energy drives the explosive expansion that inflated our early universe from microscopic to cosmic scales in almost no time at all. What happens when unstoppable expansion meets an eventual stop? The inflaton field doesn't maintain its energy forever. It gradually rolls down from high energy to low energy, like a ball rolling down a hill. But this isn't a steep cliff that drops straight down. The energy landscape looks more like a very gentle slope that goes on for a long distance. This creates what scientists call slow roll conditions. As long as the field energy decreases slowly, inflation continues to drive expansion. The universe keeps growing exponentially while the field gradually loses power. But when the field finally reaches the bottom of its energy hill, inflation stops abruptly. The timing of this roll-down determines how long inflation lasts. A gentler slope means longer inflation and a larger final universe. A steeper slope means shorter inflation and less total growth. Our universe's current size suggests the slope was just right. After inflation ends, the universe faces a strange problem. All that expansion energy has to go somewhere. The inflaton field can't just disappear into nothing. Instead, the field does something remarkable. It breaks apart and transforms its energy into the familiar particles and radiation that fill our cosmos today. This transformation is called reheating. Think of it like a massive firework that explodes into thousands of smaller sparks. The inflaton field decays into photons, electrons, quarks, and all the other particles that make up normal matter. This process floods the universe with intense heat and creates the conditions for the hot Big Bang. Without reheating, inflation would just leave behind a cold, empty universe with nothing in it. The reheating process provides all the raw material that eventually forms stars, galaxies, planets, and everything else we observe. Why does the universe look so perfectly flat? This question puzzled scientists for decades. A curved universe should either collapse quickly or expand so fast that nothing interesting could happen. Inflation provides an elegant answer. Imagine drawing a small circle on a deflated balloon. The circle looks curved and obvious when the balloon is small. But inflate that balloon to enormous size and something amazing happens. The same circle now appears completely flat to anyone standing on its surface. The curvature is still there, but it's been stretched so thin that it becomes undetectable. This is exactly what inflation did to space itself. Any initial curvature in the early universe got stretched to such enormous scales that we can't measure it anymore. From our perspective inside the inflated universe, space appears perfectly flat because inflation expanded it far beyond the size where curvature matters. The cosmic microwave background shows the same temperature everywhere you look. But these distant regions should never have been able to communicate with each other. Light from one region couldn't reach another in the time available. This creates the horizon problem that we discussed in the previous chapter. How did disconnected parts of the universe end up with identical properties? Inflation solves this puzzle brilliantly. Before inflation began, these now distant regions were actually close neighbors. They had plenty of time to reach the same temperature when they were sitting right next to each other. Then inflation grabbed this small uniform region and stretched it to cosmic proportions. What we see today as opposite sides of the observable universe were once parts of the same tiny neighborhood. They share the same temperature because they started as one connected region before inflation separated them. Every galaxy, star, and planet in the universe started as a quantum fluctuation smaller than an atom. This sounds impossible, but inflation makes it work. But quantum mechanics says that energy fluctuates randomly at microscopic scales. These tiny ripples appear and disappear constantly in empty space. Normally, they're far too small to matter for anything bigger than subatomic particles. But inflation changes everything about scale. When space expands exponentially, it stretches these quantum ripples from atomic to cosmic size. What began as microscopic energy variations became the density differences that eventually collapsed into galaxies and stars. The process works like blowing up a photograph until individual pixels become visible. Inflation took quantum scale fluctuations and expanded them until they became the seeds for all cosmic structure. Without these amplified quantum ripples, our universe would be perfectly smooth and completely empty. Scientists don't just theorize about inflation. They can actually observe its effects in the cosmic microwave background radiation. This ancient light carries the imprint of those inflated quantum fluctuations like cosmic fingerprints. The pattern of hot and cold spots matches inflation theory's predictions with stunning accuracy. The evidence is written across the entire sky. Satellites have mapped these temperature variations to incredible precision. The size, shape, and distribution of the fluctuations all match what inflation theory predicts. The statistical properties of the ripples even confirm specific details about how inflation worked. These observations provide some of the strongest evidence for any theory in cosmology. The cosmic microwave background doesn't just support inflation, it validates the idea that quantum fluctuations grew into cosmic structures through exponential expansion. Scientists haven't discovered just one version of inflation theory. They've developed dozens of different models that all produce similar results through different mechanisms. Some models, called chaotic inflation, assume the inflaton field starts with random energy values everywhere. Other models, called new inflation, require the field to begin in a specific state. Each approach makes slightly different predictions. The models vary in how long inflation lasts, how it starts, and how it ends. They propose different energy scales, different field properties, and different triggers for the expansion, yet they all solve the same fundamental problems with the standard Big Bang theory. This diversity is actually a strength. It shows that inflation isn't dependent on one particular set of assumptions. Many different mechanisms can produce the exponential expansion needed to explain our universe's current properties. Imagine shrinking down to the smallest possible size that has any meaning in physics. This isn't just really small. This is the absolute limit where the concept of size itself stops working. Scientists call this the Planck length. It's about 20 decimal places smaller than a proton. At this scale, quantum mechanics and gravity become equally important for the first time. This creates an impossible situation for physics. Quantum mechanics describes the behavior of tiny particles. General relativity describes the behavior of massive objects in space-time. These two theories work perfectly in their separate domains, but they give completely contradictory predictions when both apply simultaneously. At the Planck scale, both theories must work together to describe reality, yet neither can accommodate the other's basic principles. Physics needs entirely new concepts to function at this fundamental level. How fast do things happen at the universe's beginning? Events occur so quickly that normal ideas about time completely break down. The shortest meaningful interval of time is called Planck time. This represents the time it takes light to travel one Planck length. It lasts for an impossibly brief instant. During this period, both quantum mechanics and relativity matter equally. Think of it this way. For most of cosmic history, gravity dominates large-scale behavior while quantum effects stay hidden at microscopic scales. But during the Planck era, these two forces meet head-on with equal strength. This creates a realm where space-time itself behaves according to quantum rules. Time stops flowing smoothly and starts jumping in discrete quantum steps. The familiar concepts of before and after lose their clear meaning. You think of space as smooth and continuous, like a perfectly flat sheet of paper. But quantum mechanics suggests something far stranger happens at the smallest scales. Space and time themselves start fluctuating wildly when you zoom in far enough. Random bubbles of space-time pop in and out of existence constantly. The smooth fabric of reality breaks apart into what physicists call quantum foam. These fluctuations destroy the very meaning of distance and duration. At the Planck scale, asking how far or how long becomes like asking what color is Wednesday. The questions themselves stop making sense because the concepts they depend on no longer exist. This quantum foaming creates a fundamental barrier to understanding the universe's origin. Before physics can describe what happened at the beginning, it must first figure out how to describe spacetime when spacetime itself is breaking apart. What if space isn't smooth at all? What if it's actually made of tiny, discrete pieces connected together like links in a chain? Loop quantum gravity approaches this problem by treating spacetime as a network of quantum relationships. Instead of smooth geometry, space becomes a collection of discrete nodes connected by quantum links. This creates a fundamentally grainy structure for reality itself. Think of the difference between a photograph and a computer screen. From far away, both look smooth and continuous. But zoom in close enough and you see the individual pixels that make up the digital image. Loop quantum gravity suggests that spacetime has pixels too. This discrete structure automatically prevents the mathematical infinities that plague other approaches. When space comes in minimum-sized pieces, density can't become infinitely large because there's a limit to how much matter can fit in the smallest possible volume. What if the fundamental building blocks of reality aren't particles at all? String theory proposes that everything in the universe is made of incredibly tiny, vibrating strings. These strings are far smaller than any particle we've ever detected. They exist in 11 dimensions instead of the 3 dimensions of space we experience. Different vibration patterns create different particles. It's like having a cosmic guitar with strings so small you can't see them. When a string vibrates one way, it creates an electron. When it vibrates differently, it creates a photon or a quark. All the particles and forces in nature emerge from the various ways these fundamental strings can wiggle. String theory automatically includes gravity as one of these vibration patterns. This makes it a candidate for the unified theory that could describe both quantum mechanics and general relativity within a single framework. Can you build space-time from nothing but cause and effect relationships? Causal set theory says yes. This approach treats space and time as collections of discrete events connected by causal links. An event can influence another event only if it comes before it in the causal chain. Space emerges from the pattern of these causal connections. Think of it like building a city from scratch using only the relationships between locations. You don't start with streets and buildings. You start with rules about which places can influence which other places. The geography emerges naturally from these influence patterns. In causal set theory, the smooth space-time we observe is like looking at a city from far away. Up close, you see the discrete events that make up the urban landscape. From a distance, these events blend together to create the continuous space and time of everyday experience. Here's a radical idea. What if gravity isn't actually a fundamental force? What if it emerges from something more basic, like temperature emerges from the motion of atoms? Emergent gravity theories propose that gravitational attraction is actually a collective effect of many underlying quantum processes. Just as heat is the average motion of countless molecules, gravity might be the average effect of countless quantum interactions. This would completely change our understanding of cosmic origins. If gravity is emergent, then the extreme conditions at the universe's beginning might not involve gravity in the way we usually think about it. The fundamental level of reality could operate according to completely different principles that only produce gravitational effects under normal conditions. This approach suggests that the singularity problem disappears because gravity itself doesn't exist at the most fundamental level. The mathematical breakdown occurs only when we mistakenly apply emergent concepts to the underlying quantum reality. Your entire three-dimensional world might be a projection from a two-dimensional surface. This sounds like science fiction, but serious physicists take the holographic principle very seriously. The principle states that all the information contained in any volume of space can be represented on the boundary surface of that volume. It's like having a hologram where the three-dimensional image contains no more information than the two-dimensional film. This has profound implications for the universe's origin. If our three-dimensional cosmos is actually encoded on a two-dimensional boundary, then the extreme conditions at the Big Bang might not be as extreme as they appear. The apparent compression of infinite matter into zero volume becomes a much more manageable problem when the real action happens in fewer dimensions. The holographic principle suggests that the universe's beginning is like watching a 3D movie. The drama appears to happen in 3 dimensions, but the real information is stored in the 2-dimensional projection system. Classical physics predicts that matter must collapse to infinite density at the Big Bang, but quantum mechanics has a different opinion about what happens under extreme compression. Quantum effects become stronger as matter gets squeezed into smaller spaces. At some point, these effects become powerful enough to push back against gravitational collapse. This creates a quantum bounce instead of a classical singularity. Think of compressing a spring. Classical physics would let you compress it to 0 size if you had enough force, but real springs push back harder as they get compressed. Eventually, the spring force overcomes the compressing force and pushes everything back out. Quantum effects work similarly for gravitational collapse. They create a repulsive pressure that prevents infinite compression. Instead of forming a singularity, the universe bounces from contraction back into expansion. Quantum mechanics describes individual particles using the Schrödinger equation. But what equation describes the quantum state of the entire universe? John Wheeler and Bryce DeWitt attempted to answer this question by applying quantum mechanics to the whole cosmos. Their equation treats the universe itself as a quantum system. But this creates a bizarre problem. The resulting equation has no time parameter. In normal quantum mechanics, the Schrödinger equation describes how quantum states change over time. But the Wheeler-DeWitt equation describes a universe where time doesn't flow at all. This suggests that time is not fundamental to the deepest level of reality. What we experience as temporal flow might be an emergent property that only appears when we observe small parts of the universal quantum state. The universe as a whole exists in a timeless quantum superposition. Stephen Hawking proposed something remarkable. What if time doesn't have a beginning or end? What if the universe's history forms a closed loop with no sharp edges? The no-boundary proposal suggests that asking what came before the Big Bang is like asking what's south of the South Pole. The question assumes a boundary that doesn't actually exist. This eliminates the need for a moment of creation. In Hawking's model, time curves back on itself near the universe's origin. Space and time form a smooth, closed surface like the surface of a sphere. Just as the Earth's surface has no edge or boundary, the universe's space-time has no beginning or end. This proposal uses imaginary time, a mathematical concept from quantum mechanics, to create smooth geometry where classical physics predicts singular breakdown. The universe exists eternally in a state that includes what we call its beginning as just another point in space-time. Can the universe literally create itself from absolutely nothing? Quantum tunneling suggests this might be possible. In quantum mechanics, particles can tunnel through energy barriers that classical physics says they can't cross. A quantum particle can spontaneously appear on the other side of a wall without having enough energy to climb over it. The same principle might apply to the entire universe. Some theories propose that our cosmos tunneled into existence from a state of pure nothingness, not empty space, which still contains vacuum energy, but absolute nothing. No space, no time, no energy, no laws of physics. This quantum tunneling from nothing doesn't violate energy conservation because the total energy of the universe might actually be zero. The positive energy of matter and radiation exactly cancels the negative energy of gravitational fields. Creating something from nothing becomes possible when that something has zero total energy. Every expanding balloon eventually stops growing if you let the air out. The same fate might await our universe. After billions of years of expansion, cosmic growth could reverse and start contracting instead. This reversal would create the opposite of the Big Bang. Scientists call it the Big Crunch, a cosmic compression that squeezes everything back into a single point. The entire universe would collapse under its own gravitational weight. Imagine watching a movie of cosmic expansion played in reverse. Galaxies that are racing apart today would start moving toward each other. Stars would merge into dense clusters. Matter would compress into increasingly smaller volumes. Eventually, all space would shrink to zero size, reaching the same impossible conditions that existed at the Big Bang. This creates the possibility that the collapse itself could trigger a new expansion, starting the entire cosmic cycle over again. What if our three-dimensional universe is actually a thin slice floating in higher dimensional space? This radical idea suggests that multiple universe slices exist parallel to each other in dimensions we cannot perceive. Sometimes these cosmic slices collide with tremendous force. Each collision creates what we experience as a Big Bang, followed by expansion, then eventual collision with another universe slice. This process repeats indefinitely through cosmic history. Think of soap bubbles floating in air that occasionally bump into each other. When two bubbles collide, they can merge violently or bounce apart with great energy. Equiradic theory proposes something similar happens with universe membranes in higher dimensions. Each collision releases enormous energy that inflates our three-dimensional space from nearly nothing to cosmic scales. The collision also sets up conditions for future collisions, creating an endless cycle of cosmic death and rebirth. Breathing follows a natural rhythm of expansion and contraction. Your lungs inflate with air, then deflate, then inflate again in an endless cycle. The universe might follow a similar breathing pattern on cosmic scales. In cyclic cosmology, the universe alternates between periods of expansion and contraction over vast time scales. Each complete cycle lasts hundreds of billions of years. This creates an eternal cosmic rhythm with no beginning or end. During the expansion phase, galaxies form and evolve much like our current cosmic era. But eventually, expansion slows and reverses into contraction. The universe shrinks back toward a dense state, then bounces into a new expansion phase. This breathing cycle continues forever, with each breath representing a complete cosmic epoch. Our current expanding universe is just one exhalation in an infinite sequence of cosmic breaths. A phoenix burns to ashes, then rises again with renewed life. Some cyclic universe models work similarly. Each cosmic death leads to rebirth with completely different properties. Instead of repeating identical cycles, each new universe operates according to different physical laws. The strength of gravity changes. Particle masses shift. The speed of light varies. Every cosmic rebirth becomes a fresh experiment in physics. Picture a deck of cards being reshuffled after every game. The same basic elements exist, but they combine into entirely new patterns each time. The Phoenix universe reshuffles the fundamental constants of nature with each cycle. This means the universe we inhabit might be just one variation in an infinite series of cosmic experiments. Previous universes might have operated under completely different rules that made stars impossible or atoms unstable. Classical physics predicts that cosmic compression leads inevitably to a singularity, a point of infinite density where all physics breaks down. But quantum effects might save the universe from this fate. When matter gets compressed beyond a certain threshold, quantum forces push back with enormous strength. This creates a cosmic bounce instead of continued collapse. Think of jumping on a trampoline. The fabric stretches down under your weight until elastic forces overcome gravity and launch you back upward. Quantum gravity works similarly during cosmic compression. As the universe contracts toward maximum density, quantum effects create repulsive pressure that halts the collapse. This pressure then drives the universe back into expansion, starting a new cosmic cycle. The bounce mechanism eliminates the mathematical singularities that plague other cyclic models. Instead of infinite compression, the universe reaches a minimum size, then rebounds smoothly into its next expansion phase. Mathematicians can describe how the universe's size changes over time using something called a scale factor. This number tracks whether space is expanding, contracting, or staying the same size. In cyclic models, the scale factor follows a wave-like pattern that repeats over cosmic time. The universe grows to maximum size, then shrinks to minimum size, then grows again. This creates a mathematical function that looks like a sine wave extending infinitely in both directions. Imagine graphing the height of ocean waves over time. The water level rises to a peak, falls to a trough, then rises to another peak in a regular pattern. Cyclic universe models predict similar regular oscillations in cosmic size. Each complete oscillation represents one full cosmic cycle from maximum expansion through contraction and back to maximum expansion. The mathematical pattern continues forever, with no first cycle or final cycle. Every process in nature tends to create more disorder over time. Ice cubes melt, hot coffee cools down. Organized systems become disorganized. This tendency toward increasing disorder is called entropy. Each cosmic cycle would produce more entropy than the previous cycle. Over many cycles, disorder would accumulate until the universe becomes too disorganized to function normally. This entropy buildup makes perfect cosmic cycles impossible. Think of a wind-up toy that runs down a little more with each use. Even if you wind it up again, it never quite returns to its original condition. Eventually, the mechanism wears out completely. Cyclic universes face the same problem. Each cycle adds irreversible disorder to the cosmic system. After enough cycles, the universe would become so entropy-laden that stars couldn't form, chemistry couldn't work, and complex structures couldn't exist. About 70% of the universe consists of dark energy, a mysterious force that currently drives cosmic expansion. But the properties of dark energy might change over cosmic time. If dark energy weakens sufficiently, gravitational attraction could overcome cosmic expansion and reverse it into contraction. If dark energy then strengthens again, it could halt contraction and restart expansion. Changes in dark energy properties could drive the cosmic cycle. Picture a car with a gas pedal that sometimes accelerates and sometimes brakes. The same mechanism controls both speeding up and slowing down, depending on how you use it. Dark energy might work similarly, sometimes accelerating cosmic expansion, sometimes allowing or even driving cosmic contraction. The transitions between these modes could create the rhythm that drives cyclic universe models. Scientists are searching for evidence that our universe has gone through previous cycles. They look for subtle signatures in the cosmic microwave background radiation that might reveal pre-Big Bang activity. Some models predict specific patterns in temperature fluctuations or polarization that would indicate cyclic history. Others suggest that gravitational waves from previous cycles might still be detectable. The challenge is distinguishing cyclic signatures from other possible explanations. Think of archaeologists searching for artifacts from ancient civilizations. They must carefully separate genuine historical evidence from natural formations that might look similar. Cosmologists face the same challenge when searching for cyclic signatures. They must demonstrate that observed patterns actually come from previous cosmic cycles rather than from other physical processes that occurred since the Big Bang. If cosmic cycles are real, can information survive from one universe to the next? Some cyclic models suggest that certain properties carry forward through the cosmic recycling process. This would create a form of cosmic heredity where each universe inherits characteristics from its predecessor. The physical constants, field configurations, or structural patterns might pass from old cosmos to new cosmos. Such continuity would connect all cosmic cycles into one extended evolutionary sequence. Imagine a family business passed down through generations. Each generation brings new innovations, but core traditions and methods continue from parent to child. Cyclic universes might work similarly. Information about previous cosmic cycles could influence how the next cycle develops. This creates a cosmic memory that spans multiple universe lifetimes, linking past and future cosmic eras through inherited properties. If the universe goes through endless cycles, when did the cycling begin? This question creates a logical puzzle called infinite regress, an endless chain of causes that never reaches a first cause. Every cycle requires a previous cycle to explain its origin, but the previous cycle also needs a predecessor. This reasoning continues backward infinitely without ever finding a starting point. The infinite regress problem challenges the logical foundation of cyclic cosmology. Picture standing between two mirrors that face each other. Your reflection bounces back and forth infinitely, creating an endless series of images. But this infinite series doesn't explain where the original person came from. Cyclic universe models face the same logical difficulty. They explain cosmic evolution as an infinite sequence of cycles, but cannot account for why cycling exists in the first place. The explanation becomes circular, requiring what it sets out to explain. Inflation doesn't have to end everywhere at the same time. While our region of space finished inflating long ago, other areas might still be expanding explosively right now. Think of inflation like popcorn cooking in a giant pan. Some kernels pop early and stop growing. Others keep popping continuously. The pan itself keeps getting bigger as more and more kernels join the process. This creates what scientists call eternal inflation. Once inflation begins in any region of space, it tends to continue forever in most places. The expanding space creates more room for the inflattened field to work. More field energy means more expansion. More expansion means even more field energy. This becomes a runaway process that feeds on itself. While inflation ends in some lucky pockets like ours, it continues indefinitely in the vast majority of space. New regions are always joining the inflationary party. When inflation finally stops in a small region, something remarkable happens. That region becomes completely cut off from the still inflating areas around it. These isolated zones develop into what physicists call pocket universes. Each pocket follows its own independent evolution. It develops its own stars, galaxies, and physical laws. Each pocket becomes a separate cosmic reality. The space between these pocket universes keeps expanding so rapidly that they can never communicate with each other. Light from one pocket can never reach another pocket because the space separating them grows faster than light can travel. From inside any pocket universe, the inhabitants would think their pocket is the entire cosmos. they would have no way to detect the existence of other pocket universes. Each pocket represents a complete, self-contained world. Sometimes the vacuum of space decides to change its fundamental properties. This process works like water suddenly turning into ice, but with much more dramatic consequences. The vacuum can exist in different energy states, like water existing as liquid or solid. When vacuum transitions from a higher energy state to a lower energy state, it releases enormous amounts of energy. This energy release can trigger the birth of an entirely new universe. Scientists call the higher energy state a false vacuum because it looks stable but isn't really the lowest possible energy state. When false vacuum finally decays to true vacuum, it creates expanding bubbles of new spacetime. Each bubble becomes the seed for a new cosmic realm with potentially different physical laws. The decay process happens randomly, so new universes can pop into existence at any time without warning. Our universe operates according to specific physical constants. The strength of gravity, the mass of particles, the speed of light. But what if these constants could be different? String theory suggests that countless different combinations of physical laws are possible. These form what scientists call the cosmic landscape, a vast map of potential realities. Each point on this landscape represents a different possible universe. Some regions of the landscape might have stronger gravity. Others might have different particle masses or force strengths. Most combinations would create universes where nothing interesting happens. Stars can't form, atoms fall apart, or space itself becomes unstable. But within this enormous landscape of possibilities, some regions create universes capable of supporting complex structures. Our universe represents just one working solution among countless failed experiments. Why does our universe seem perfectly tuned for life? The physical constants appear fine-tuned to incredible precision. Change them slightly and stars can't form, atoms become unstable, or chemistry becomes impossible. This apparent fine-tuning puzzled scientists for decades. It seemed like cosmic luck on an impossible scale. But the multiverse provides a simple answer. If countless universes exist with different physical laws, then some will inevitably support life while most will remain barren. We necessarily find ourselves in one of the rare universes that allows observers to exist. This creates a selection effect similar to winning the lottery. It's not that the lottery was rigged in your favor. It's that only lottery winners get to wonder about their luck. Similarly, only universes capable of producing observers will ever be observed. How do you calculate probabilities when you're dealing with infinite quantities? This seemingly simple question creates one of the most serious problems in multiverse theory. In eternal inflation, infinitely many pocket universes form over time. Some types of universes appear more frequently than others, but comparing infinite quantities leads to mathematical nonsense. Any finite number divided by infinity equals 0. This means you can't determine which types of universes are more or less likely to exist. Every possible outcome happens infinitely often, making probability calculations meaningless. Scientists call this the measure problem. Without a way to assign meaningful probabilities to different universe types, the multiverse theory becomes impossible to test or verify through any kind of statistical analysis. String theory doesn't predict just one possible universe. It predicts an astronomical number of different universes, each with unique physical properties. The theory requires extra dimensions beyond the 3 we experience. These dimensions can be curled up in countless different ways, like origami folded into different shapes. Each folding pattern creates a different possible universe. Scientists estimate that string theory allows for something like 10 to the 500th power different universe types. That number is so large it makes the number of atoms in our observable universe look tiny by comparison. Most of these string universe possibilities would be completely inhospitable to any kind of structure or life. But among such a vast menu of options, some would inevitably create the conditions we observe in our own cosmic neighborhood. Universes can give birth to other universes in a cosmic family tree. Parent universes create child universes through various quantum processes. When a new pocket universe forms through false vacuum decay, it inherits some properties from its parent while developing other characteristics independently. This creates a branching structure of cosmic relationships. Some child universes might be nearly identical to their parents. Others might have completely different physical laws. The parent universe continues existing while spawning multiple offspring universes over time. This process can continue indefinitely, with child universes eventually becoming parents themselves. The result is an ever-growing family tree of cosmic realities, each branch representing a different experimental approach to physics and chemistry. Most things need external help to make copies of themselves. Photocopiers need electricity. Plants need seeds and soil. But eternal inflation reproduces using only its own internal processes. Inflation creates more space. More space provides more volume for the inflaton field to operate. More field activity drives more inflation. The process becomes self-sustaining without any outside intervention. This makes inflation remarkably similar to biological reproduction. Like a living organism, inflation copies its essential features into new regions of space. Each new region inherits the ability to inflate further. The original inflating region continues its own expansion while spawning countless copies. Unlike biological reproduction, cosmic self-reproduction never runs out of materials or energy. The process can continue indefinitely, creating an ever-expanding family of related cosmic regions across infinite space. How do you test a theory about universes you can never observe? The multiverse concept creates a fundamental problem for scientific methodology. Science works by making predictions and checking them against evidence, but other universes are permanently beyond our observational reach. We can never gather direct evidence about their existence or properties. This pushes multiverse theories beyond the traditional boundaries of experimental science. Some scientists argue that theories which can't be tested aren't really scientific theories at all. They become mathematical exercises or philosophical speculations rather than empirical science. Others believe that indirect evidence and theoretical consistency can substitute for direct observation. The multiverse concept might be scientifically valid even if it can never be directly verified through conventional experimental methods. Empty space refuses to stay perfectly still. Even when you remove every last particle, every photon, every trace of matter and energy, the vacuum still buzzes with invisible activity. This restless behavior comes from one of quantum mechanics' most fundamental principles. It's called the uncertainty principle, and it says that energy and time cannot both be perfectly defined at the same moment. This uncertainty creates constant fluctuations in the fabric of reality itself. Think of it like a calm lake that looks perfectly smooth from far away. But get close enough and you see tiny ripples and waves constantly disturbing the surface. The vacuum of space behaves similarly. It appears empty from our perspective, but see this with quantum activity at the smallest scales. These fluctuations aren't just theoretical curiosities. They produce measurable effects that scientists can detect in laboratory experiments. The vacuum's restless energy influences the behavior of atoms and particles in subtle but observable ways. Quantum mechanics allows particles to borrow energy from the universe's bank account, as long as they pay it back quickly enough. These borrowed energy particles are called virtual particles. Virtual particles pop into existence in pairs, exist for incredibly brief moments, then annihilate each other before anyone can catch them red-handed. It's like cosmic bookkeeping with extremely strict deadlines. The more energy a virtual particle borrows, the faster it must disappear to avoid violating conservation laws. High-energy particles get only the tiniest fraction of a second to exist. Lower-energy particles can stick around slightly longer. This constant creation and destruction of virtual particles fills every cubic centimeter of apparently empty space. They interact with real particles, influence the forces between objects, and even create measurable pressure between closely spaced metal plates. In the classical picture, absolute zero temperature means all motion stops, all molecular vibration ceases, all thermal energy disappears. But even at this ultimate cold, quantum systems retain a minimum amount of energy. Scientists call this leftover energy the zero-point energy. It represents the irreducible quantum jitters that persist even when classical physics says everything should be perfectly still. This minimum energy exists in every quantum system throughout the universe. Imagine trying to balance perfectly on a tightrope. Classical physics would let you stand motionless if you had perfect control. But quantum mechanics says you must always wobble slightly, no matter how hard you try to stay still. The zero-point energy of all quantum fields throughout space adds up to an enormous total. Some calculations suggest this vacuum energy density exceeds the energy density of matter by more than 100 orders of magnitude. The vacuum of space might not be as stable as it appears. What we think of as empty space might actually be a false ground state, a temporary resting place that could suddenly shift to something completely different. Think of water that stays liquid even below freezing temperature. It looks stable and permanent until a single ice crystal triggers the entire volume to freeze instantly. Our vacuum might be similarly precarious. If the vacuum exists in a metastable state, a random quantum fluctuation could trigger a transition to the true ground state. This transition would spread outward at the speed of light, fundamentally altering the laws of physics as it passes. Inside the expanding bubble of true vacuum, particles might become unstable, forces might change strength, or matter itself might cease to exist. The transition would be invisible until it arrived, offering no warning and no escape. Quantum particles can pass through energy barriers that classical physics says are absolutely impassable. This process, called quantum tunneling, works like a coin that occasionally passes through a solid table. The probability of tunneling depends on the height and width of the energy barrier. Higher barriers make tunneling less likely. Wider barriers also reduce the chances of success. The same tunneling process might apply to the creation of entire universes. If our cosmos exists inside a false vacuum state, quantum tunneling could trigger the birth of new universe bubbles. Each bubble would represent a fresh cosmic experiment with potentially different physical laws. Scientists can calculate the tunneling probability for universe creation. Though the numbers are incredibly small, even tiny probabilities become significant when you have infinite time and infinite space for attempts. Stephen Hawking and Ayn Moss discovered a mathematical pathway for universe birth through quantum tunneling. Their solution describes how a universe can spontaneously appear from a pre-existing de Sitter space. De Sitter space represents a universe filled with pure vacuum energy. It expands exponentially like inflation but contains no matter or radiation. The Hawking-Moss instanton shows how this empty, expanding space can give birth to matter-filled universes. The process works through quantum fluctuations that temporarily create regions of different vacuum energy. Most fluctuations collapse back to the original state, but occasionally, a fluctuation grows large enough to trigger a permanent transition. This mathematical description treats universe creation as a quantum mechanical process similar to radioactive decay. Individual creation events are unpredictable, but the overall rate follows statistical laws. Sidney Coleman and Frank DeLucia solved the equations for how new universes nucleate inside existing space. Their work describes the formation of expanding bubbles that become independent cosmic domains. Picture blowing soup bubbles in the air. Each bubble starts small but grows rapidly once it forms. The Coleman-DeLucia process works similarly but with space-time instead of soap. Each bubble becomes a separate universe with its own interior physics. The bubble walls expand at nearly the speed of light, but the space inside each bubble inflates even faster. This rapid interior expansion creates room for matter and energy to develop according to the local physical laws. From inside any bubble, inhabitants would observe their region as a complete universe. They would have no way to detect the larger space containing their bubble or the existence of other bubble universes nearby. Some quantum theories suggest that black holes might give birth to baby universes through microscopic wormholes. These cosmic offspring would develop completely independently from their parent universe. The wormhole connection acts like an umbilical cord that eventually gets severed, leaving the baby universe to evolve on its own. Each baby universe inherits some characteristics from its parent while developing unique features through its own evolution. Think of it like biological reproduction, where offspring share some parental DNA but develop their own distinct traits. Baby universes might have similar physical constants to their parents but different particle types, force strengths, or space-time geometries. The baby universe process could create an infinite family tree of cosmic generations, with each universe potentially spawning multiple offspring during its lifetime through black hole formation and collapse. What does it mean for absolutely nothing to exist? This question pushes the boundaries of both physics and philosophy into territory where language itself breaks down. True nothingness would contain no space, no time, no energy, no physical laws, no mathematical structures, and no potential for anything to happen. Yet quantum mechanics suggests that even this absolute nothing might be unstable. The challenge lies in defining nothingness precisely enough to apply physical theories to it. If nothing has no properties, how can it be subject to quantum fluctuations? If nothing has no time, how can anything emerge from it? Some physicists argue that absolute nothingness is logically impossible because the concept of nothingness requires some framework to define what is absent. Others propose that quantum mechanics operates even in the absence of space-time. Quantum mechanics describes individual particles using mathematical objects called wave functions. These functions contain all possible information about a system's quantum state. But what mathematical object describes the quantum state of the entire universe? physicists have proposed a universal wave function that encompasses all possible cosmic histories. This cosmic wave function would be the ultimate recipe book for reality itself. The universal wave function doesn't describe just one universe with definite properties. Instead, it describes a quantum superposition of all possible universes with all possible physical laws, particle types, and cosmic histories. According to this view, every conceivable universe exists simultaneously within the universal quantum state. What we experience as our specific reality represents just one component of this vast quantum superposition. How can the universe create itself from absolutely nothing without violating the fundamental law of energy conservation? The answer lies in a remarkable feature of gravitational energy. In many cosmology treatments, gravitational energy is treated as negative. When matter clumps together under gravity, the total energy of the system actually decreases. This negative gravitational energy can cancel the positive energy of matter and radiation. The universe's total energy might be precisely zero. If the universe's net energy equals zero, then creating it from nothing doesn't violate energy conservation. The positive energy of all matter, radiation, and motion exactly balances the negative energy stored in gravitational fields. This zero-energy universe concept makes spontaneous creation mathematically possible. The universe becomes the ultimate free lunch, a vast cosmic structure that costs nothing to create and maintain because all its energy accounts balance perfectly. Remove all change from the universe and something strange happens to time. No particles moving, no energy flowing, no processes occurring anywhere. In such a completely static reality, the concept of time loses all meaning. Time doesn't exist independently of the events that mark its passage. Without change to measure, duration becomes an empty word with no reference point. This creates a fundamental problem for understanding cosmic origins. Think of trying to measure speed when nothing moves. The concept of velocity requires both distance and time intervals. Remove all motion and speed becomes meaningless. Similarly, time requires change to give it substance and definition. If the universe began from a state of absolute nothingness, there were no changes to define temporal intervals. The question, what came before the Big Bang, assumes that time extends backward beyond the first moment of change. But time itself might be impossible without something changing to mark its flow. Stephen Hawking discovered a mathematical method for eliminating the Big Bang singularity. His approach uses something called imaginary time, a concept borrowed from quantum mechanics that treats time like a spatial dimension. Imaginary time doesn't correspond to anything you can directly experience. It's a mathematical tool that allows physicists to calculate quantum processes that would be impossible in ordinary time. When Hawking applied imaginary time to cosmic origins, the singularity vanished completely. Picture the North Pole on Earth. In ordinary coordinates, it represents a singular point where longitude lines converge. But switch to different coordinates and the North Pole becomes just another smooth point on a curved surface. Imaginary time works similarly for the Big Bang. The apparent singularity at cosmic origins becomes a smooth geometric point in this mathematical framework. The universe has no beginning or end, just a closed, finite boundary like the surface of a sphere. What if past, present, and future all exist at the same time? Einstein's relativity suggests that our sense of now is just an illusion created by our limited perspective. According to the block universe model, all moments in cosmic history exist equally. The dinosaur extinction, your birth. and events billions of years in the future all have the same degree of reality. Time becomes like space, a dimension we can move through, but that exists in its entirety. Imagine viewing a movie reel as a physical object. Each frame exists simultaneously as part of the complete film. Your experience of watching the movie creates the illusion that only one frame exists at any moment. But the entire story is always there. If the block universe model is correct, asking what came before the Big Bang is like asking what's west of the westernmost frame in a movie. The question assumes a perspective that doesn't match the actual structure of reality. Could time be like temperature? Temperature emerges from the average motion of countless individual molecules, even though individual molecules don't have temperature themselves. Similarly, time might emerge from some more fundamental, timeless reality. The underlying structure of existence could operate without any temporal dimension, yet give rise to our experience of temporal flow. This would make time a collective property rather than a basic feature of reality. Consider how wetness emerges from H2O molecules. Individual water molecules aren't wet. Wetness appears only when many molecules interact together. The molecules themselves follow timeless chemical laws, but their collective behavior creates temporal phenomena. If time is emergent, then the universe's origin occurs outside the temporal framework entirely. The fundamental level of reality would be described by timeless principles that don't require any before or after to operate. What if causation is more fundamental than space and time? Instead of events happening within a pre-existing space-time framework, maybe causal relationships create the framework itself. This approach treats cause and effect connections as the building blocks from which space and time emerge. Space-time geometry becomes a consequence of how events can influence each other. The causal structure determines what we experience as space and time. Think of building a city based purely on transportation connections. You don't start with a map and then add roads. You start with rules about which locations can connect to which other locations. The geography emerges from these connection patterns. In causal structure theory, the Big Bang represents the first causal event, the beginning of influence relationships rather than the beginning of time. Before this first cause, there were no causal connections to define temporal or spatial relationships. When physicists try to write the Schrödinger equation for the entire universe, something bizarre happens. The resulting equation, called the Wheeler-DeWitt equation, contains no time parameter at all. This suggests that the universe as a whole exists in a completely timeless state. What we experience as temporal evolution might be an illusion that appears only when we observe small parts of the cosmic quantum state. The fundamental description of reality contains no flowing time. Imagine taking a photograph of a flowing river. The photograph captures the entire scene at once. There's no motion or time flow in the image itself. Yet the image contains information about the river's flow patterns. The Wheeler-DeWitt equation treats the universe like such a photograph. The fundamental quantum state contains all possible cosmic histories simultaneously, without any built-in temporal direction or evolution. Zoom into the Planck scale and time stops behaving like the smooth, continuous flow we experience. At these incredibly tiny distances and brief intervals, time becomes choppy and uncertain. Quantum effects make it impossible to measure time intervals shorter than Planck time. Below this threshold, the very concept of temporal sequence becomes meaningless. This creates a natural boundary for questions about cosmic origins. Picture trying to measure the thickness of soap bubbles using a ruler made of bowling balls. The measuring tool is far too crude for the delicate structure you're trying to examine. Similarly, our time-based questions become too crude for the quantum scale where cosmic origins occur. At the Planck scale, space-time itself becomes uncertain and fluctuating. The smooth temporal flow that allows before and after questions simply doesn't exist at the fundamental level where the universe begins. Maybe time doesn't exist as an absolute background against which events occur. Perhaps time emerges only from the relationships between different events and objects. In relational time theory, temporal intervals arise from comparing how different systems change relative to each other. There's no universal clock ticking away independently, only relative changes between physical systems. Time becomes a measure of relationships rather than a fundamental dimension. Consider how we actually measure time in practice. We compare the rotation of Earth to atomic vibrations or heartbeats to seasonal cycles. Every time measurement involves comparing one changing system to another changing system. If time is purely relational, then asking what came before the Big Bang assumes there was some external reference frame to measure before against. But without any physical systems to create temporal relationships, the concept of before becomes undefined. Why does time seem to flow in only one direction? The answer might lie in the tendency for disorder to increase throughout the universe. The second law of thermodynamics states that entropy, roughly speaking, the amount of disorder, tends to increase over time. This gives time a natural direction from less disordered states toward more disordered states. The thermodynamic arrow provides time with its forward direction. Think of a movie played backward. You immediately notice something wrong when you see smoke flowing into chimneys, broken glass reassembling, or water flowing upward. These processes violate the natural increase of disorder. If entropy increase defines time's direction, then the Big Bang represents the lowest entropy state possible. Before this minimum disorder state, there was no basis for defining which direction is earlier versus later in time. Quantum mechanics suggests that measurement plays a fundamental role in creating definite reality from indefinite possibilities. Before measurement, quantum systems exist in superposition, multiple potential states simultaneously. The act of measurement collapses these multiple possibilities into one actual outcome. This collapse process might be intimately connected to the emergence of temporal flow. Time might exist only in the process of converting quantum possibilities into classical realities. Imagine a story that exists in draft form with multiple possible endings. The story becomes definite only when someone chooses one ending and discards the others. Similarly, the universe might exist as quantum possibilities until measurement processes select specific outcomes. If time emerges through quantum measurement, then the universe's origin involves the first measurement-like process that began converting infinite possibilities into definite reality. Human language evolved to describe temporal experiences. Every verb implies time. Every sentence assumes a sequence of subject-verb-object relationships unfolding in temporal order. This creates a fundamental barrier to describing timeless reality. We have no linguistic tools designed for discussing truly atemporal phenomena. Our language forces temporal assumptions onto every description we attempt. Try explaining color to someone who has been blind from birth. You quickly discover that visual concepts require visual experiences to be meaningfully understood. Similarly, explaining timeless reality requires conceptual tools that transcend temporal experience. When physicists attempt to describe quantum gravity or cosmic origins, they must use time-based language to discuss timeless phenomena. This linguistic limitation might make certain aspects of reality fundamentally indescribable rather than scientifically unknowable. Some questions appear meaningful, but actually contain hidden logical errors. Asking what came before the Big Bang might be one of these misleading questions. A category error occurs when you apply concepts from one domain to another domain where they don't belong. It's like asking what color Wednesday is, or how much freedom weighs. The question about cosmic origins might commit this same type of logical mistake. Consider asking what's north of the North Pole. The question seems reasonable until you realize it assumes a geographic framework that doesn't extend beyond Earth's northernmost point. Similarly, asking what came before the Big Bang assumes a temporal framework that might not extend beyond cosmic origins. If time itself began with the Big Bang, then before has no meaning in this context. The question dissolves not because we lack information, but because it requests something that cannot logically exist. Scientists dream of finding one master equation that explains everything in the universe. This theory would unify all forces, predict all particles, and answer every fundamental question about physical reality. Such a theory of everything would finally reveal what existed before the Big Bang. It would merge quantum mechanics with general relativity into a single, elegant mathematical framework. But this ultimate prize continues to elude even the most brilliant minds. Think of trying to solve a jigsaw puzzle when you're missing crucial pieces. You can see parts of the picture clearly, but the complete image remains frustratingly incomplete. Physics faces the same challenge on a cosmic scale. Current theories work beautifully within their separate domains, but refuse to fit together into a unified whole. Each new discovery reveals more complexity, rather than the elegant simplicity that a theory of everything should provide. The conditions that existed at the universe's beginning require energies that dwarf anything humans can create. The most powerful particle accelerators on Earth produce energies trillions of times weaker than what's needed. Building machines capable of reproducing cosmic origin conditions would require resources beyond any conceivable technology. You would need accelerators larger than galaxies powered by the energy output of entire stars. These energy scales place fundamental limits on what experiments can test. Imagine trying to study ocean waves using a bathtub. The physics might be similar, but the scale differences make direct comparison impossible. Laboratory physics operates in a completely different energy regime than cosmic origins. This experimental gap forces scientists to rely on indirect evidence and theoretical speculation rather than direct empirical testing. The most important questions about reality remain forever beyond the reach of controlled scientific investigation. There exists a fundamental limit to how far back in cosmic history we can observe. This boundary isn't created by weak telescopes or insufficient technology. It's built into the structure of space-time itself. Beyond this observational horizon, the universe becomes permanently invisible to any form of detection. No signal, no information. No evidence can reach us from these hidden regions. This creates an absolute ceiling on empirical knowledge about cosmic origins. Picture standing in a dense fog that extends infinitely in all directions. No matter how perfect your eyesight or how powerful your flashlight, you can never see beyond where the fog begins. The cosmic observational horizon works similarly. The first moments after the Big Bang remain shrouded behind this impenetrable veil. Direct observation stops at this boundary, leaving the universe's true beginning forever hidden from empirical investigation. Sometimes the same evidence can support completely different theories equally well. This creates a troubling situation where scientific data cannot decide between competing explanations. Multiple theories about cosmic origins make identical predictions for all observable phenomena. Yet these theories propose radically different mechanisms for how the universe began. This leaves scientists unable to determine which explanation is actually correct. Consider three witnesses describing the same accident from different angles. Each provides accurate but incomplete information. You might construct several different stories that all fit the available evidence perfectly. Cosmic origins face this same underdetermination problem. The limited evidence we can gather allows multiple contradictory theories to remain viable. Scientific method alone cannot resolve which theory describes reality accurately. Science advances by testing theories against evidence and rejecting those that fail. But many theories about cosmic origins make no testable predictions that could prove them wrong. A theory that cannot be disproved might not qualify as genuine science. It becomes more like mathematics or philosophy, intellectually interesting but empirically unverifiable. This challenges the fundamental principles of scientific methodology. Imagine playing a game where no move can ever be declared illegal. Without rules that eliminate wrong answers, you're not really playing a game with definite outcomes. Science faces similar difficulties with non-falsifiable theories. String theory, multiverse concepts, and many quantum gravity approaches suffer from this testability problem. They might represent profound insights about reality, or they might be elaborate mathematical fantasies with no connection to the physical world. Even when scientists have the right equations, solving them requires computational power that exceeds current capabilities by enormous margins. Quantum gravity calculations involve mathematical complexity that overwhelms the fastest supercomputers. The equations contain so many variables and interactions that complete solutions would require computing resources larger than the observable universe itself. This creates a bottleneck between theoretical understanding and practical calculation. Think of having a perfect recipe for a meal, but lacking the equipment to prepare it. You know exactly what ingredients and steps are needed, but you cannot execute the process with available tools. Quantum gravity faces this same computational barrier. Scientists understand the mathematical principles involved, but cannot perform the calculations needed to extract specific predictions about cosmic origins. New detection methods are pushing the boundaries of what we can observe about the early universe. Gravitational wave detectors might eventually sense ripples from cosmic inflation itself. Advanced measurements of cosmic microwave background polarization could reveal signatures of quantum gravity effects. Space-based telescopes might detect primordial gravitational waves from the universe's first moments. These future observations could provide the first direct evidence about cosmic origins. Picture archaeologists developing new tools that let them examine older and deeper layers of ancient civilizations. Each technological advance reveals previously hidden information about the past. Similarly, advancing detection technology continues, extending our observational reach toward earlier cosmic epochs. Future instruments might finally pierce the veil that currently hides the universe's beginning from direct observation. Artificial intelligence is beginning to tackle problems that overwhelm human cognitive abilities. Machine learning systems can detect patterns in complex data that escape human notice. I might eventually discover relationships between quantum mechanics and general relativity that human physicists have missed. Computer algorithms could identify solutions to equations that traditional analytical methods cannot solve. This opens new possibilities for understanding cosmic origins through artificial intelligence. Consider how microscopes revealed stellar structures invisible to naked eyes. AI serves as a cognitive microscope that might expose theoretical structures invisible to human reasoning alone. Machine intelligence operates without the conceptual limitations that constrain human thinking. AI systems might develop entirely new approaches to quantum gravity that transcend traditional physical intuition. Throughout scientific history, revolutionary discoveries have made previous questions obsolete. What seemed like fundamental problems suddenly became irrelevant after conceptual breakthroughs. A sufficiently radical advance in physics might reveal that asking what came before the Big Bang is like asking how many angels can dance on a pinhead, a meaningless question based on false assumptions. Future paradigm shifts could transform our entire approach to cosmic origins. Think of how the discovery that Earth orbits the Sun made previous debates about celestial mechanics obsolete. The new framework didn't just provide different answers. It showed that many old questions were asking about non-existent problems. Similarly, breakthrough insights about the nature of time, space, causation, or existence itself might dissolve current puzzles about cosmic beginnings. The questions that seem so important today might appear quaint and misdirected from future perspectives. Some questions about cosmic origins push beyond the boundaries of empirical science into philosophical territory. Issues of ultimate causation, the nature of existence, and the meaning of nothingness require more than scientific methodology. These questions involve fundamental assumptions about logic, mathematics, and the relationship between mind and reality. They cannot be resolved through observation and experimentation alone. This creates a boundary region where scientific knowledge meets philosophical speculation. Picture two countries that share a border with a disputed territory between them. Neither country has clear authority over this intermediate zone, yet both have legitimate interests there. Science and philosophy face similar boundary disputes about cosmic origins. Questions about ultimate reality require insights from both empirical investigation and conceptual analysis. The complete picture emerges only when scientific and philosophical approaches work together.